With the pandemic still raging, we haven't been able to go outside, meet our friends at the park whenever we want, go on sunny vacations, and have been stuck inside our homes, or what now feels like a dark and lonely cave of endless work. And without the bright yellow circle called the sun, we are unable to produce one of the most essential nutrients for a healthy life, vitamin D. So what is this thing called vitamin D? Simply put, vitamin D, or cholecalciferol, is a key organic nutrient that we produce ourselves in the skin with the help of sunlight. It plays crucial roles in the maintenance of our immune system by activating white blood cells, maintains bone health by regulating calcium homeostasis through activating channels which increase calcium intake in our intestines, absorbs harmful radiation from the sun, and many more important roles. As well, it is a key ingredient in the making of rodenticide, as it elevates blood calcium to toxic levels when consumed by smaller organisms like mice. Of course, all this would not be possible without vitamin D's metabolic mechanism and physical properties on the chemical level. But before we dive deeper into its chemistry, let's see how this sunshine vitamin was discovered and was finally recognized of its importance. The discovery of cholecalciferol was not an easy task and required multiple revisitations and disprovals of previous works. The vitamin-related diseases of rickets, scurvy, and beriberi were very prevalent throughout the world, but its causes were still a mystery until scientists had finally decided to look into them in the early 20th century. One of the first to study these vitamin-related diseases was a scientist named Christian Dijkman, who found that adding hulls of rice to the diets of Dutch prisoners had seemed to help lower their beriberi incidence. From this, he concluded that polished rice had a beriberi-causing toxin, which then the hulls had neutralized. Later on, Gerrit Griggens had revisited Dijkman's research and correctly demonstrated that the hulls had contained an essential nutrient which had prevented beriberi, rather than inhibiting an unknown toxin. However, this nutrient being what we now know as vitamin A wasn't identified, as the concept of vitamins had yet to be born. So then, this had kick-started the research into vitamins, and a new chapter of biochemistry had begun. Now, Sir Edward Malomby from Great Britain had been investigating the high incidence of rickets in Scotland and deduced that it could be due to a certain type of dietary deficiency. To prove his hypothesis, he got a few dogs, fed them a similar diet of the Scottish people, and then placed them indoors away from sunlight. And this caused the dogs to actually develop rickets, and since cod liver oil had proved to cure this, he concluded that it was vitamin A that was responsible. Elmer McCollum, however, questioned this discovery and carried out experiments at Johns Hopkins University. He bubbled oxygen gas through the cod liver oil, which destroyed the vitamin A, and then he tested it again. Surprisingly, the result was still successful in curing rickets and had led to the discovery of a new vitamin, vitamin D, or cholecalciferol. However, it wasn't until the 1930s that the structure of vitamin D and its precursors were identified by multiple scientists, and they had also correctly concluded that the active form of vitamin D would only be present through the irradiation of its inactive state, 7-dehydrocholesterol. Now, let's move on to the more exciting portion, vitamin D's chemistry. So, to start off, its IUPAC name is 1S3Z32E21R3AS, and oh my god, this is way too long of a name. So let's just appreciate the beauty of common names and call it cholecalciferol. As with all vitamins, cholecalciferol is an organic compound which contains a total of 27 carbons, some of them being in cyclic structures and others in linear structures. The major structures of cholecalciferol are the A-C-D rings and the linear heptane tail. The A ring is a cyclohexane which has a hydroxyl group attached on its third carbon. The C ring is another cyclohexane while the D ring is a cyclopentane, and the two are merged together. The heptane tail has a methyl group on the 6th carbon, and as suggested from its IUPAC name, it bridges from the rest of the molecule from its 2nd carbon. As well, since there are no other functional groups with a higher priority, the hydroxyl group on the 3rd carbon makes the overall molecule an alcohol, hence its name cholecalciferol. Now moving on to Vesper, the overall shape of the molecule cannot be defined as it's a combination of many different Vesper arrangements. In terms of its bond orbitals, cholecalciferol contains both sp3 and sp2 hybridizations. sp3 hybridized carbons have a tetrahedral geometry which forms 4 sigma bonds with its 4 electron domains and has an ideal bond angle of 109.5 degrees. During hybridization, one of its electrons in the s orbital is promoted to the p orbital. Then, as the atom reaches stability, new hybridized orbitals are formed with an energy greater than s but lower than p orbitals. Meanwhile, sp2 hybridized carbons have a trigonal planar geometry which forms pi bonds on the same plane as the adjacent atoms and has ideal bond angles of 120 degrees. Similarly, one of its electrons from the s orbital is promoted to the p orbital. However, as the atom stabilizes, one p orbital remains unhybridized, while lower energy hybrid orbitals forms with the remaining 3. So from this, we can deduce that the heptane tail contains carbons with sp3 hybridization with ideal angles of 109.5 degrees, while the triene portion has carbons with sp2 hybridizations with ideal angles of 120 degrees. The hydroxyl group has a bent shape due to oxygen's 2 lone pairs. Additionally, in cyclic structures, the bond angles are all slightly less than their ideal angles due to the presence of adjacent groups and repulsion from their electron densities. So for example, cyclopentane's angles range from 107 to 106.2 degrees, while its ideal angle would be 108 degrees. Now, for intramolecular forces, there are only covalent bonds present in cholecalciferol between its carbons and other nonmetals. This is when 2 atoms share a common electron density to achieve a stable valence octet. The bond lengths are as shown, and the respective bond strengths are as shown as well. For intermolecular forces, cholecalciferol is able to form 3 types: hydrogen bonds, London dispersion forces, and dipole-dipole interactions. For hydrogen bonding, the hydroxyl group allows for hydrogen bonding as a dipole forms due to oxygen's high electronegativity. For London dispersion forces, the long hydrocarbon chain creates instantaneous dipoles, allowing for temporary attractive forces between each other. And for dipole-dipole interactions, the polar hydroxyl group is at clash with the non-polar hydrocarbon chain, which produces dipoles on either side of the molecule. For cholecalciferol's physical properties, its molar mass is an astonishing 384.64 grams per mole, and this is expected from an organic compound with 27 carbons. It is white, odorless, and a solid powder. Its density is 1.0 plus minus 0.1 grams per centimeter cubed. Its melting point is 84.5 degrees Celsius, and its boiling point is 496.4 degrees Celsius. And both melting and boiling points are very high due to the strong London dispersion forces from large temporary dipoles from the large hydrocarbon chains. As well, since it's an alcohol, it forms hydrogen bonds, which is the strongest intramolecular force possible, between each other, resulting in very high thermal points. In water, it is insoluble, but it's slightly soluble in vegetable oil and also in ethanol and methanol. It's not soluble in water due to the overwhelmingly longer non-polar hydrocarbon chain, but it will dissolve in alcohols due to miscibility. And you may think, why is it insoluble in water but soluble in alcohols if They're both polar molecules, and this is because alcohols are amphiphilic. It contains both polar and nonpolar ends, thus it is able to dissolve both polar and nonpolar solutes. So now let's talk about how vitamin D is synthesized. So the first is a photochemical reaction which converts 7-dehydrocholesterol into pre-vitamin D. And this is when UVB light from the sun has enough energy to dismantle the B ring in 7-dehydrocholesterol by breaking the bond between the 9th and 10th carbon to form 2 additional double bonds on either side and result in the pre-vitamin D3 intermediate. Next, their pre-vitamin D3 undergoes thermal isomerization to form cholecalciferol, and this is when, without absorbing additional photons and needing to be in an excited state, the molecule uses its own kinetic energy to isomerize into its active form. So here it being the change from a cis to trans isomer with a rotation of the bond between the 6th and 7th carbon. To calculate the energetics of cholecalciferol, I had used the bond enthalpies as provided in the IB chemistry data booklet. So for the average bond enthalpy of cholecalciferol, I had got the sum of all the bond enthalpies present in the molecule and then divided it by the number of bonds in the molecule. So for cholecalciferol, that gave me 398 kilojoules per mole. I also did the same for methane to compare, and I got 414 kilojoules per mole. And for a more accurate comparison, I used percentage difference, so that gave me around 4.02%, and it being that much more difficult to break methane's bonds when compared to cholecalciferol's. For its molar enthalpy of combustion, I had used the same bond enthalpies and used the formula which subtracted the sum of the bond enthalpies formed from the sum of the bond enthalpies that were broken. So this gave me a number of negative 15,652 kilojoules per mole, and this means that 15,652 kilojoules per mole of energy is released when 1 mole of cholecalciferol is burned. Now moving on to reactions, the first is hydroxylation, which is when an alkane is oxidized into an alcohol. So in the liver, the enzyme 25-hydroxylase oxidizes the 25th carbon of cholecalciferol, making it 25-hydroxyvitamin D3. Hydroxylation occurs once again in the kidneys, where 1-monoxygenase hydroxylizes the first carbon, making it 1-alpha 25-dihydroxyvitamin D3. The next is secondary alcohol oxidation. When the hydroxyl group is examined, we can see that it is bonded to a carbon with 2 other adjacent carbons. Thus, cholecalciferol can be described as a secondary alcohol. So with an oxidizing reagent in heat, the alcohol is oxidized into a ketone. Unlike primary alcohols, the reaction stops as there are no more hydrogens to remove. And last but not least is the rearrangement reaction. So now let's look at what really happens in thermal isomerization during vitamin D synthesis. You may have noticed that there is only one major difference between pre-vitamin D3 and cholecalciferol, and that is its shape. This is due to the sigmatropic rearrangement, where a sigma-bonded hydrogen between 1 or more pi bonds shifts to a new location and thereby causing a rearrangement of the pi bonds. So here, in our case, a shift from the 19th carbon to the 9th carbon in pre-vitamin D3 causes its shape to change from the cis conformer to the trans conformer, as evidenced by the bridge straightening out between the 6th and 7th carbon, and therefore becoming its active form, cholecalciferol. It's also important to note that this mechanism is reversible when there are enough active vitamin D3s in circulation. So hopefully by now you've gained some insight into the sunshine vitamin, And make sure to go take walks outside like I did here and synthesize plenty of vitamin D.